second lecture of Fourier series. We will discuss further theorems related to this topic. Next one is, if function is bounded and integrable on the interval minus pi to pi and a and bn be the Fourier coefficients, then we have to prove that this sum converges. To prove this result, we are taking the term minus pi to pi fx minus summation an cos nx plus bn sin nx whole square of this term. As we know that the square of any term is always greater than or equal to 0. So we are taking the square of this term greater than or equal to 0. Then by applying the formula of a minus b whole square, we get this term minus pi to pi f square plus minus pi to pi square of second term, then minus 2ab. Then by using the previous results, if we apply a plus b whole square on this term, then we get square of this term plus square of this one plus 2ab. When in the case of square of the first term, we get an square cos square nx. An square is constant, so take this term outside the integral, and we are left with the term minus pi to pi cos square nx dx. As we proved in the previous slides, I showed you the slide. In this case, this integral is pi, and for cos is also equal to pi. So in that proof, we get the value of first term equal to pi, so we are left with pi an square. Similarly for second one, the value is also pi, so we are left with pi bn square, and the term 2ab, that becomes 0 because the integral cos nx sin nx is equal to 0. In this case, this term minus pi to pi fx cos nx, this is the value of the Fourier coefficient pi an. Similarly, this is the value of the Fourier coefficient pi bn. An is already there, so this term becomes pi an square and this becomes pi bn square. After compiling these terms, we get this one. Then limit lambda approaches to infinity, summation an square plus bn square is less than or equal to 1 upon pi integral minus pi to pi fx dx. As the function is integrable as given in the statement, so f square is also integrable. So function is integrable, so this is convergent. If right hand side of the above inequality is convergent, then by comparison test, left hand side is also convergent. Then next result. Next one is Riemann-Lebesgue theorem. It states that if a function is bounded and integrable on any interval and capital A and Bn are defined as these values, then both approaches to 0 as n approaches to infinity. In this proof, we are taking the two cases. First one is when small a and b both belong to the same interval of this type, and we are defining the function fx as this one. Then an, which is given as integral a to b phi x cos nx, is equal to minus pi to pi fx cos nx, as fx is defined in the above inequality. So this value is equal to pi an. As we know from the formula of Fourier coefficient, this is equal to pi an. Similarly, bn is pi bn. As a small a and bn both approaches to 0 as n approaches to infinity, so these coefficients also approaches to 0 as n approaches to infinity. Similarly, we can prove the second case when both a and b do not lie in the same interval. This theorem is a naming theorem. Its statement is very important for the short notes. You can remember this statement for short answer questions. Next article, if a function is bounded and integrable in the interval 0 to a, where a is in positive number, and monotonic in the interval 0 to delta, where delta lies between 0 to a, then limit n approaches to infinity, integral fx sin nx by x dx is equal to this term. In this case also we are taking the two cases. First one we are taking f when f of 0 positive is 0, or we can say that f of 0 is 0. Then we are using the second mean value theorem to calculate the value of this integral 0 to delta fx sin nx by x dx is equal to this one by second mean value theorem. As f of 0 is 0, so first term becomes 0, we are left with the second one only. In the second integral we are substituting nx is equal to t. Integral changes to this form. As we know that this integral is always convergent, so this term is less than or equal to t. This result comes from the improper integrals. Therefore, n delta 1 to n delta sin x by x dx, we are breaking this integral into two integrals, n delta 1 to 0, 0 to n delta. Then we are changing the limits of first integral, it becomes negative by a triangular inequality. Split the modulo of these two terms. As from the above equation, this integral of this type is less than or equal to k, so both these modulo are less than or equal to k, so we get right hand side of the equation as 2k. After this we get this equation number 2. Also f of delta approaches to 0 as delta approaches to 0 positive, because we are taking the case when f of 0 positive is 0. So modulus of this function is less than epsilon. In place of epsilon we are taking epsilon by 4k. Then finally the term which we are taking, this one, take modulus on both sides, we get modulus of this term, modulus of f delta, modulus of second integral. Modulus of integral is less than or equal to 2k, and modulus of f delta is less than epsilon by 4k. We are substituting values from equation number 2 and 3 in this inequality. We are left with the epsilon by 2. So this integral becomes less than epsilon by 2. Then we are taking the limit 0 to a as given in the statement fx sin nx. Split this integral into two integrals, 0 to delta and delta to a. Since the second integral on the right hand side approaches to 0, this comes from the previous theorem, Riemann-Lebesgue theorem. And so both the second integral approaches to 0, so we can take this as less than epsilon by 2. So both these integrals are less than epsilon by 2. This is less than epsilon by 2 and epsilon by 2, so this becomes epsilon. As modulus of the term becomes less than epsilon, that implies this term approaches to 0. Term approaches to 0 means equal to this term. As we are taking f of 0 positive equal to 0, so right hand side is also 0. Left hand side equal to 0 implies right hand side is equal to left hand side. In the second case, when f of 0 positive is not equal to 0, that implies this term is equal to 0. We are replacing f with this one, f minus f of 0 positive. Split this integral into two integrals. That this becomes the this type of two terms. F of 0 positive limit n approaches to infinity, this one. In this integral we are substituting nx is equal to t. Then change the variable. In place of t we are taking x. So this is a required statement. So this theorem is true for both cases, when f of 0 is 0 and f of 0 is not equal to 0. These are two corollaries of this theorem. These are important. You can solve these equations also for the short notes. Then next result. If function is bounded and integrable on the interval minus pi to pi and monotonic in these two intervals, then we have to prove this equation. We are taking the left hand side of the equation, this one, and substituting the values of Fourier coefficients. A naught is equal to minus pi to pi fx dx 1 upon pi, plus then the value of the an Fourier coefficient, substituting here 1 upon pi minus pi to pi fx into cos nx. Then compile these two integrals. Then open this summation as cos x plus cos 2x up to so on cos mx. We are using the formula from the trigonometry here. Then change this one to this form. These are cos A sin B formulas. You can take these formulas from the trigonometry. This term becomes this one. Then take LCM sin x by 2. After taking LCM, we get this equation. First term cancel out with the third one. We are left with this term only. Then split this integral into two integrals. Minus pi to pi a changes to minus pi to 0, 0 to pi. In the first integral, change x to minus x. This becomes, then change x to 2x. We can change x to minus 2x in the one step also. Then take m approaches to infinity. After taking m approaches to infinity, these two integrals changes to this one. When m approaches to infinity, this function we can take as f of 0 negative. This function becomes f of 0 positive, and we are left with 0 to infinity sin x by x dx. When we take fx is equal to 1, then a naught becomes 2 and an becomes 0. Then from equation number 1, this is the case. So finally the integral becomes 2 upon pi 0 to infinity sin x by x dx. You can solve these steps on your notebook. Then, as we know that 0 to infinity sin x by x dx is pi by 2, then substitute the value of the integral in the right hand side. This is our required result. In the next theorem, we are given that the function is bounded, periodic with period 2 pi. Then we have to prove this equation. All these steps are same as in the previous theorem. We are substituting the values of the coefficients, Fourier coefficient, value of a naught, then value of an, value of bn. Then compile these equations, compile these integrals, then open this summation, then changes this sum into its formula with the help of trigonometric formulas. Same steps are here. Then in place of fx, we are here f of x plus I. Everything is same. Steps are totally same. So finally, we get the result of this theorem. These two theorems are totally same. Only the function is replaced with f of, in place of fx, we are taking f of x plus I. You can solve these steps on your notebook to clarify the theorem. Then there are some corollaries. This is the corollary of the theorem. This is all. After these theorems, all theorems are very important. One theorem comes in the long answer questions. From 4 to 5 theorems, one theorem always come in the examination for the long answer questions, and their statements are also important for short ones. After these theorems, in the next lecture we will discuss the examples of Fourier series, how we can calculate a Fourier series of a function.